We move on to neural networks next, and I don't have the patience to teach you what they are. But don't worry, I know just a person to do it. Take it away, Radu.
Neural networks are computing systems inspired by the biological neural networks in our brain.
These are some neurons.
These branch-like structures receive the signals. When stimulated enough, a neuron will fire a signal through its axon. So a single neuron does something really simple, and intelligence only comes when they work as a team. You see, your brain has 86 billion neurons. You also have quite many of them in your spinal cord and sensory organs, like in your eyes and ears. These sensors send signal to some neurons that pass it to the brain. There, the processing happens like a chain reaction where some neurons fire, some don't, eventually signals arriving to motor neurons that pass them through your spinal cord and make some muscles contract in very specific ways. Hey! A lot happened in just a split second. Let me try to slow this down and explain it to you. Pay attention.
Hey!
Sensors inside the ear pick up compression waves from the air and send signals to the brain, which figures out the direction based on different intensities. Signals then travel to neck muscles, tell them to contract and turn the head in that direction. The eye catches a glimpse of what's happening, and new signals travel to the brain. Peripheral vision is blurry, but good enough information exists to detect some kind of object approaching, and new signals travel to facial muscles to contract and protect the eyes from getting hurt. Eyes are really important. At the same time, the brain begins a kind of defense protocol by sending signals throughout the body. Time passes and the image becomes more clear. The brain does pattern matching and recognizes the object as a ball. Contextual and historical information will play an important role in what happens next. Let's stick to the first one. The brain concludes there is no threat and uses knowledge about physics it learned during its lifetime to predict where the object is headed. It then sends new signals to the muscles to contract in slightly different ways to catch the object instead of blocking it. And the rest is history. One history where the brain did a good thing and not much happens afterwards. But sometimes this happens, and the brain learns it did something wrong and configures itself so the same thing doesn't happen again. Hopefully. Anyway, I'm feeling really good about myself now that I know my brain can do something like that in an instant. Hope you do too. Our car's neural network will do something like that. Neurons on the first layer will be connected to the sensors. They will send signals forward a few times. And the last layer will be connected to the car controls to make it actually do something. Spoiler alert, we'll be working with relatively small networks here. But that's okay, because we actually don't need very large networks to solve this problem.
Now that you have a basic idea, take the code from the link in the description. You'll need it to follow along. But beware, I will just briefly go through it. And if you really want to understand it, go watch these two videos first. Of course, watching the whole self-driving car series is even better. There is one thing about what Radu said in the beginning that bugs me.
So a single neuron does something really simple.
I got this comment from Mikhail, and I should point out that biology is really not that simple. We don't fully understand how brains work to this day. But a simple model like that is all we need to build an artificial neural network. I definitely don't want you to draw the wrong conclusion, and that comment made me think twice about my wording. Get it? Think, because a neural network no.
Gonna code, debug, and have fun. Coding with Radu. Coding with Radu. Gonna prototype and design. Coding with Radu. Coding with Radu. Let's code now.
I've added the two files here. In common, we have network.js now. And in web.js, we also have viewer.js here. Viewer.js is pretty much the same as in that tutorial, except that I made these output labels be images now. There I used emojis, but here I wanted to use the colored emojis we generated earlier. And there are a few other small tweaks here and there, but pretty much the same code as you've seen there. And network.js here is the same code from the tutorial with this small difference here instead of how it was originally written. Because in the self-driving car case, the car could press two keys at the same time, like maybe accelerate and go to the left. But here we need to decide which is going to be the winning class. So we're leaving these outputs as the raw value there. And we will select the class to be the maximum value that we get. I've also added here this export so that it fits with our current structure. But other than that, it's exactly the same. We have here the neural network made out of different levels, the level having inputs, outputs, biases, and the weights. We have methods for randomizing these weights and biases because that's how we knew to optimize in that other course. We just tried randomly different networks and hoped for the best. We kept the best one all the time. Then the feed-forward algorithm just implements that summation and outputs all the outputs. The feed-forward for the whole network just feed-forwards each individual level like that. And the only difference is really this line of code here. But if you've watched that tutorial, you know what it means. Now, to use this new code, we will build a new classifier next to our KNN classifier that we had here already. And I'm going to copy this one for reference. Let's copy and paste it here with a new name. I will rename this file MLP.js. MLP stands for Multilayer Perceptron. And I think it's a good name here because neural network is kind of like NN from here, so I want to keep this different, and it will also match with what we do in Python later on. Now we will modify this code inside of MLP.js. So here we have MLP now, and let's export here also MLP, like so. And I'm going to empty here the constructor. We won't save the samples here. This model doesn't store the samples. It's what makes it much more efficient than this k-nearest neighbor. Let's remove them from here as well. And I'm going to empty also this predict method, but I will keep the return so that we know what structure we need to return things in. Now, the constructor is going to take as parameters the neuron counts. We need to know how many neurons we should use, and also the classes. The model needs to know what are the options. Let's save these here as attributes of this MLP. So the classes. And now let's initialize a neural network with the code from the file we just added and pass here the neuron counts. So this we need to include here, same as we include utils, but here we include the neural network, like so, from the network.js file. And the prediction here is what changes. We just get the output from the neural network's feed-forward algorithm when we pass this point, the parameter from here, and this network that is stored as the attribute of the class right here. From these outputs, we calculate the maximum. So let me use math, max, and spread here, this output array. And let's get the index of the element with the maximum, like so. And the label of that is going to be taken from classes at that index. Simple as that. Now, for consistency with the KNN, I will keep here an object with the attribute label, but we don't have any nearest samples here. It's gonna be null. Let's save this file, and to evaluate this MLP model, I'm going to copy here in Node the run evaluation. So let's copy this, paste it here, and we will have two run evaluations. One will be with KNN, and the other one will be with MLP, like so. So let's modify this run evaluation MLP. And the first thing we do here at the top is rename our classifier to MLP, like that. And then reading it here from MLP.js. And here where we initialize our model, we don't have KNN. Instead, we have MLP. And this MLP is going to take the two parameters. First, the neuron counts. And we have 5 features at the moment. So the first neuron count is going to be 5. And the second one is going to be, let's just say, directly the outputs. And we have 8 different outputs. The car, fish, house, tree, bicycle, guitar, pencil, clock. And the second parameter we pass are the classes, which are here. And these hard-coded values, we don't have to keep them hard-coded. We can just replace here 5 with taking the training samples first item there, the point, and the length of that point. And here is just the length of these classes. So now we don't have to change these anymore. They will work as expected. So this is a neural network without a hidden layer. It just connects the inputs to the outputs directly. And we will experiment with hidden layers later here. You could pass a hidden layer with maybe 10 neurons and another one with 10 neurons and one with 5 and so on. But at the moment, we don't. We just have this simple connection. Now let's copy this and replace every time we want to do a prediction KNN with MLP, and here also. That's it. Now let's run this new evaluation. I'm going to start the terminal, make sure we're in the node directory, and node run evaluation MLP this time. And it's really fast. I didn't speed up the video this time. It's also not very good. This accuracy here is random chance. If you've done homework 7, then you know this is random chance. And Leo Caesar 3D mentioned this in a comment. Now, because this is based on randomness when we add the weights and biases, every time we run this evaluation, we will get a different value here. Sometimes we're more lucky than others because the networks that we are getting just happen by chance to be a good or a bad configuration. In the self-driving car course, we experimented with many different networks and choosing the best. So let's try to do that here as well. We will try to fit the network to the training data. So let's open our MLP file here and implement a new method here called fit. The samples, now we pass the samples to this because it's going to need them, but it's not going to store them. It's just going to update the weights and biases according to these samples somehow. You'll see. And we'll use the same strategy of randomness and trial and error. We will try, for example, 1,000 times and keep the best network that came. So let's consider the best network being the one in the class attributes. and the best accuracy. Let's evaluate that network on the samples. Now we are evaluating on the training data. We are not yet seeing testing data, but we're trying to improve the model. This is okay. I'm going to now loop through this number of tries, and let's try to generate a new network. After we do that, we evaluate its accuracy on the training samples. And if it's better than the best accuracy, we keep it. And we also keep the network like so. Now here at the end, we just set this network to the best one that we've found. And we still need to implement this evaluate method here. It's not complicated. All we have to do is implement the method like that and count how many of them are correctly predicted when we loop through all of the samples, take out the label, and remember here to destructure, because that's what MLP predict will return on the sample point. Now, the true value for this is what is stored in the sample label. We know the true labels for our samples. But if this predicted label here matches the truth, then we increase the correct count. So correct count increases if truth is equal to label 1, otherwise it doesn't increase. And here we just calculate the accuracy by dividing correct count by samples length. And let's return this accuracy. Let's save this file, and in a run evaluation MLP, after we initialize the MLP classifier here, we fit it to the training data. So MLP fit training samples. And let's try this again. I'm going to open now the terminal and rerun the evaluation MLP. Now we get 26.8, which is much better than the random chance things we were getting previously. So it is working. We are searching through 1,000 networks. And if we're going to increase here maybe by, 5,000, then this accuracy should be even better, because now it's trying even harder. It's going through even more. It's an expectation, but of course you can be really unlucky with those 5,000 randomly generated networks, and then it's not going to look so good. And it doesn't really make sense once we have found a good one like this to go back down to a crappier one. So what we could do is save this model every time we find it, and then load it when we do this optimization, so we can continue a previously made optimization with the saved network as a basis. Let's save this model. So I'm going to type here write file sync, and we will need the constant for where the model should go. And then I'm just going to stringify the whole MLP object, and that's it. Now, I want this model to be accessed also by the web page so that we can try the neural network there as well. And I'm going to use the same structure here, putting model.js also as a constant, and here initializing a variable called model, and then putting this stringified JSON inside of it. And now let's close this template literal, like so. Now these constants need to be added. I'm going to go here in constants.js, and let's copy this one for the decision boundary. This is going to be model now, and it's going to be in this models directory. Let's call it model.json. And the JS object, let's just copy this min-max here. And this is going to be model.js and model.js. Now, when we are going to run this evaluation, this model with 31.96% accuracy is going to be saved in data model here next to the decision boundary. And if I'm going to format it, you will see it has the neuron counts information, the classes information, and the network with all the levels, which is just one level for this one. And we have the inputs, the 5 different features, the outputs, the result of the feed-forward algorithm, and here the biases and the weights from all the inputs to all the outputs. Now, the inputs here and the outputs here are just the last values that have been used in the training process. They are meaningless. Every time you do a classification, these will become overwritten with whatever the features are, and these here are going to become generated from the feed-forward algorithm. They're now just placeholders here, and that's okay. Now, if we want not to lose this model and get at least 31.96% accuracy in the next model, we have to load this one. So in run evaluation MLP, after we do this initialization, let's load it from that file before we do the fitting. So let's say here, if that file exists, the one that contains the model, I'm going to mlp.load and parse it after we read it. Like so. Now this load is a really simple method that we still need to implement here inside of MLP.js. I'm going to do it just below the constructor here and load. Given an MLP model, I'm just going to update this model's neuron count to that one's. And the same thing for the classes. And the same thing for this network. It's basically a copy constructor. Now let's save this and rerun the evaluation. And the same accuracy as before. We didn't get lucky with the 5,000 tries here, but if we try again, still no luck. If we try again, still nothing. Still nothing. But now it worked. So we could optimize like this. It would take quite a long time to reach the same level accuracies that we are getting with our KNN. There are better optimizers than this trial and error out there, and we'll try those later. But now let's get this to work on the web page as well. Let me close some of these things. And here in viewer HTML, we are going to have to import many JavaScript files. So here we need the new MLP classifier, similar to the KNN classifier. Then we also need that model, the one that we calculated on the back end. So this is here in JS objects, the JavaScript variant. Then we need the neural network code and the visualizer. Let me add this network.js here underneath utils and the visualizer here from this JS folder. Now we'll visualize this on another canvas, and I'm going to define it here inside of the chart container underneath the confusion container. So this is going to be network canvas, and it's going to be what we draw the canvas on. Let's give this a style similar to the confusion container. Inside of styles CSS, the confusion container is here. I'm just going to copy it below, rename this to network canvas, and give it a black background. Let's save this, close this file, and let's begin to work with the MLP classifier. We won't use KNN anymore in this course. I'm going to keep it here for reference, but I'm going to start using the MLP classifier. So MLP, and I will initialize it with empty and empty here for the neuron counts and for the classes, because they will be loaded from the model that we have calculated with the scripts. Now, every time we see KNN here, I'm going to comment out the line and write MLP variant below. So this happens here when we are calculating the accuracy of the testing samples, but also below for the real-time processing here. So let's copy this, comment it out, and replace KNN with MLP. So it's the same thing, but now with a different classifier. This should work already, but we are not visualizing it yet. So let me go here at the top and also do the visualization. I'm going to set the width of the network canvas to 500, and same for the height. And let's get a reference to the network context from this network canvas, like so. Now, we also need the output labels to look nice, and we can get those here after the graphics generate images. But let me just put this maybe here above the sketchpad and below the confusion, because now we have these related somehow. So we generate these output labels from the styles by looking at the values of the styles and then remapping them so we only take out the image of that style. We don't care about the color or the text, just the image component. And then we use our visualizer to draw the network on this network canvas, the network stored in our MLP classifier, and using these output labels that we just defined. We also want to update the visualization here after we do a real-time prediction, like so. And now let's save the file and we should be able to test. Refresh the page. And something looks horribly wrong. I noticed that this width and height features that we calculate for this empty canvas are -infinity and -infinity. And this is causing some problems now for this neural network. It was working okay for the KNN because it was just some coordinate. But now it's into some calculations there and it's causing some not a number to happen and problems. So let's fix those functions real quick. I knew they will become an issue at some point. So inside of this feature functions, at the top our width here, if the points are empty, if there's nothing there, I'm just going to return 0 for the width. And same thing will happen for the height as well. Now let's refresh this page and close this console. Toggle the input. And now the network does something here. It's saying that this is a car because this car node here, output value, is the highest. And you can see that as a yellow color coding here. Blue means negative values, and the least visible, they are closer towards 0. So this is very visible, bright yellow here. It means it's a high value. And it's not fantastic. 33.28%. We had much better results, but it is what we can do now with this random optimization strategy. And these here at the bottom are the features. So when we look at this, we can see a relatively high value for the width because it's a wide image. And this is the height here, which is smaller. Then this is going to be the elongation. Apparently quite a small value, but if we draw something like this, a really elongated shape, it's going to be bright. And then these final ones are the roundness value, and this is not round at all, but if we do make it round, it's going to be bright. And the last one is the number of pixels, basically. So if we would fill this space with a lot of pixels, then that one starts to light up as well. And apparently it is able to pick up that this is a clock. One thing that I still want to do is toggle the output, and this doesn't work anymore. We need to rewrite it so that we consider this one as well, not just the confusion matrix and the chart. So let me go to display.js and quickly rewrite this from scratch. And I will just say that if the network canvas is visible, then let's make this one invisible, and let's make the confusion container visible. Otherwise, if the confusion container is visible, we will make it invisible. Otherwise, we will make both of them visible again. So now we are going to toggle between the 3 items there. Let's save this, refresh, and this seems to work. Interestingly, we get a lot of zeros here. So it looks like the network that we have is really good at recognizing cars and pencils and clocks, but nothing else. So now we can see that this accuracy really doesn't tell a good story, but this confusion matrix really tells us what is really going on. The model forgot about these other things pretty much. And let's see now in this decision boundary plot. We can't really see much because it's still this high dimensional cube. But we could revert to the simple features. I like doing that. Let's go back to width and height, 2 features, and see how this decision boundary plot looks like now when using a neural network. So in feature functions, I'm just going to comment out here everything except for these width and height. And let's open the terminal And let's rerun the feature extraction. So node feature extractor.js. And now it's fast because it's not doing the pixels thing. And now we have to optimize again our neural network model. But the model that we created previously here inside of the data models is pretty good. And it's using the 5 different features. So it's incompatible with the 2 feature models that we try to create now. And we'll need to delete this for the code to work. So right-click, delete the model. And now run evaluation MLP. Should work. We got a new model with 26.38% accuracy. Now, if I run this again, it's going to try 5,000 more times and maybe get a better version. Or not. Let's try one more time, see if we're lucky. And we got 29% accuracy with this one. And you'll notice that this decision boundary plot is generated really quickly now, because doing the feed forward algorithm is much faster than doing the nearest neighbor search. So we could go in node here in the run evaluation MLP and set a higher value for this image size to get a better quality image there. Maybe 1000 is enough. Now let's rerun this. Took a bit longer, but it's done. And accuracy didn't change. So let's try to refresh. And we see now this network with just 2 nodes here, the width and the height, just 2 features and the input layer. And the output, it looks different, but it seems again the same kind of scenario with just 3 things considered: the car, the tree, and the bike. Now let's toggle again. And this is now the decision boundary plot. And it looks interesting. It has here at the top the tree section, and then the bicycle section, and then the car section. This is confusing me with the pencils, so let's go back to viewer HTML and put all the testing samples now. I'm going to comment out this filtering from here. Refresh. And now we can see this decision boundary plot. And every one of these trees here in the green region is classified correctly. Every one of these bikes here is classified correctly. And every one of these cars here is classified correctly. But a lot of misclassifications happen. There is a pencil region here. And this car is in the pencil region, so why didn't it show up in our confusion matrix? Oh, it did. It has a 1 here. I didn't notice it. And the tree should be there as well, apparently. And there it is. Herminio's house is also there, classified as a car. Nice. Now let's try one more thing and see if we can add the hidden layer here and if we get any difference. In our run evaluation MLP, at the top, let's say we are going to add 10 nodes on a hidden layer and see what happens. Because we redo this evaluation and the network that we have at the moment doesn't have those, I'm gonna have to delete again this model here. And rerun the evaluation. A bit worse accuracy. Let's try to improve it. Give it 5,000 more tries. Doesn't seem to work. One more try. Maybe we're lucky. And we are not. Let's just keep it like this and see what we have on the page. So this is how the new neural networks looks like. And if we toggle the input and we draw something really wide, you can see now this lighting up. Let's make it also tall, so this will light up. And a lot of things are lighting up here in the middle in interesting ways when these properties change. So it's a more complex model, but not a very good one. It also seems to now prioritize two things here. Let's see the decision boundary plot. Let's close this input. And I don't really see it so well. Let's keep just the decision boundary plot now here. And I'm going to add again this filter because it keeps that plot in a kind of squarish aspect ratio because that's where the pencils are. There's no Herminio's house to stretch things. So let's hide the samples and refresh, toggle the output. That's how it looks like. Let's re-add all the features one last time, now with this hidden layer there. So in feature functions, I will remove this comment from here. And here we go down and feature extractor. It's done. And now let's run evaluation MLP. Oh, I forgot to remove that model that we had last time. Delete. And now run evaluation MLP. Refresh. And now the input layer is more complex again. Still this kind of bad looking confusion matrix. And this one is unreliable now because we just showed the first two dimensions there. Now, optimizing this with the current strategy is not going to work well. You could wait for it to randomly try a bunch of different values and you could leave it overnight or something. You will get better values. But next time, I'm going to teach you how to use Python to get the values with more complex optimization algorithms.